Okay, let's start. So I'm happy to present you Laura Salvati, which is permanent at IAS, Institut d'Astrophysics Spatiale in Orsay. So she did her PhD at Rome University in working on Planck, then postdoc at IAS and in Trieste. And in 2021, she became permanent at IAS, working on cluster cosmology and active in science working group, cluster and in Euclid, cluster cross CMB correlation. Thank you.
Thank you. Thank you very much. So I hope you can hear me well. Yes, great. So it's a pleasure to be here today. It's actually the first time that I'm coming to give a seminar at TAP, so I'm a bit excited, I have to say. I was always on the other side. So today I would like to discuss with you how we can build a coherent cosmological and astrophysical model from the large scattering surface to the large-scale structure. So we are going to talk about CMB, cosmic microwave background anisotropies, but then also tracers of the subsequent evolution of the universe to try to describe, for example, the epoch of the reionization and the large-scale structure, and stress really the importance of building a unique and coherent model. So most of the results that I'm going to show you today are coming from this INR project called Batman. So you have the main collaborators here, and then I'm going to show you also some results from former PhD students at TIS. So we can start trying to give a bit of context of what we're going to talk about. What you have up here is really the an artistic view of what is the evolution of the universe from inflation to current times. And I've tried to highlight three different phases that we're going to discuss later. So the first one is the cosmic microwave background radiation. I mean, I hope that being here, you are all kind of aware of what is CMB, but it's the very first electromagnetic radiation that we can observe in the universe. We study the temperature and polarization anisotropy of this radiation, and it gives us really important information on all the primordial phase of the evolution of the universe. But then, I mean, we have that the photons of the CMB will travel from the last scattering surface towards us. And so, of course, they will interact with all the subsequent evolution of the universe. And so it means that we can use this radiation also to trace other events in the universe. And so, for example, we have the epoch of reionization. So it's the formation of first stars and galaxies that will start to reionize the medium around it. And then we can also trace the evolution of the large-scale structure as we observe the universe today. So the distributions of matter in these very like filamentary and nodes structures. Of course, when we start to dealing with reionization and large-scale structure, we have to take into account all the different astrophysical processes that might shape the galaxy formation and evolution, how the gas is distributed, etc. And so if we want to build a coherent cosmological modeling, understanding astrophysics is fundamental, basically. So what we can do is start to have a look, a very general look on CMB radiation and understand how we can improve the current analysis given the results that we have today. So I was talking before about temperature and polarization anisotropies of CMB, and what you see here are the temperature power spectrum from basically seen as from two different kinds of experiments. So in the left part, you have the very large scale range for the temperature anisotropies, and this was observed mainly by the Planck satellite. So we have a full sky coverage, and we have excellent sensitivity in this range, but of course not many information on the other smaller scales. And if we want to go to smaller scales, we need higher precision experiments, which are usually the ground-based telescopes. So, for example, the Atacama Cosmology Telescope or the South Pole Telescope. And in this case, we are looking really at higher resolution, deeper observations. So, of course, as you can see, we have high complementarity between these different kinds of experiments because we have on one hand like full sky, in the other case very deep in observation. We have different sensitivities, and here you have just an example of how the different the sensitivity for the different power spectra depending on the experiment that we are considering. But so it means that ideally, if we are able to combine these three kinds of experiments, we can really get the best constraints ever from CMB radiation. And clearly, the CMB community is really going in this direction, if you see results also from ACT and SPT collaboration, to try to push CMB science even further. So of course, I mean, if we want to combine different data sets, we have to be sure that we are homogenizing our observations, and in particular, homogenizing the model that is behind these observables. One of the things that we have to take into account is the fact that we are observing the sky in millimeter wavelength, and we take whatever it's emitting in millimeter wavelength, so it will not be only CMB. And in this plot here again, you see the temperature anisotropies in orange here or in black here, and then you have all these other signals that are different foregrounds, basically, to our analysis. In particular, these non-CMB components can be divided into two main categories. The first one are the secondary anisotropies. We are going to discuss this in details later. Basically, these are really due to the interaction of CMB photons with the subsequent evolution of the universe. So this kind of interaction will produce an impact on the CMB frequency spectrum or power spectrum. And we have, for example, the thermal and Sonaja-Sedovich effect and the lensing, so the distortion of light due to a massive object in the middle. And then we have simple foregrounds emission, so things that are emitting in millimeter wavelength but that are not impacting directly the CMB radiation. And for example, we have the cosmic infrared background that is mainly due to the thermal dust. We have radio point sources and possible cross-correlation between the different signals. So what is usually done at the level of CMB analysis is that you assume that your total signal will be, of course, the CMB, plus a modeling for all these non-CMB components that is usually done with a template that can come, from example, from numerical simulations, from observations that you might have in other wavelengths, from theoretical prediction. And then you try to basically compensate with different amplitudes to try to get your final signal at the end. But then, I mean, just to give you an idea, for the different components, we can have really different templates. So this is an example for CIB, for TSZ, KSZ, and the cross-correlation. Because, of course, they will depend on the kind of simulations that you are using to model it, on the observations, sometimes also on the input cosmology that you put in your simulations. So we have to start to worry if the choice of the template can actually impact the final results. And actually, one of the best ways to do this is to combine, indeed, the three CMB experiments that we have available up to now and try to do the full cosmological analysis. So the results that I'm showing here are, of course, just few results, and there are many details that we can discuss later. But the idea is that we are combining the most recent observations from Planck, ACT, and SPT, focusing on the use of a coherent modeling, especially for all the non-CMB components. So what you're seeing here are two triangular plots. So you have the posterior distribution for your parameters. On the left, you have cosmological parameters. On the right, you have the different amplitudes for the templates that we are considering. So if we focus on cosmology, I think there are two important results that are, kind of expected. The three experiments, if we look at them separately, provide results that are well in agreement with into sigma, given this coherent modeling of templates. So it means that we can actually combine them. And when we combine them, you can get the black results here. So you see how much we're actually tightening the constraints on the cosmological parameters. But then if we move to the amplitude part of the templates, you can really see that the three experiments are kind of pointing in the different, let's say, space of the areas of the parameter space. So possibly preferring one amplitude or another with respect to your total signal. And in particular, if we focus on the actual effect on this template. Here you have just an example of, again, all the amplitude and other parameters for the template. In the case on the left, in which you are varying only CIB. So as you can see in this case, the pointer is not really pointing, but I mean the top left part is just the amplitude of CIB, and you can see this is the main impact that we have. While on the other hand, if you vary the TSZ template, it will have impact on many other components. Because of course, I mean, once you're changing one of the amplitudes, you have to compensate with the other. But so we see that the assumption that we made on all the non-CMB components can actually impact our final understanding of the cosmological model, especially because all of these components are actually tracers of matter distribution of gas and galaxies, so they carry lots of cosmological and astrophysical information. And we have modeling and observations to actually detect this signal and so possibly improve also the TSZ analysis. And that is exactly what I would like to show you in the rest of the talk. We're going to focus on TSZ and KSZ, modeling and detections, and then come back and how can we plug them into the CMB analysis. So let's start with the very recent part of the evolution of the universe. We are going directly to the cosmic web of the large-scale structure. Here you have a depiction of the cosmic web coming from the illustrious simulations. So we know that we are in a recent universe, low redshift. We are looking at a very non-uniform and non-linear matter distribution. So we have this kind of web that is composed by peaks of galaxy clusters, then filaments, wall, and voids that are very under dense region. And the evolution of this large-scale structure is mainly driven by dark matter, so the gravitational collapse, and dark energy that will drive the accelerated expansion of the recent universe. So we would like to put constraints on these quantities, but we can only always observe the baryonic component, so the standard matter that we know. And in particular, we observe galaxies and gas. So just to give you an idea, this is how the galaxies and gas are actually tracing the underlying matter distribution. So whatever observations and studies you are doing in large-scale structures, there is always this problem, how you relate your observable, that is baryonic matter, to the underlying full distribution of cold dark matter. And of course, in building this relation, you always need to understand what are the possible astrophysical processes that will impact your distribution of observable. And one of the unique ways to do that is through the thermal Sunaya-Seldovich effect. So, as we were saying before, this is a secondary anisotropy. So it means that it's an interaction of CMB photons with the subsequent evolution of the universe. And in particular, it's an interaction between photons and electrons in hot gas reservoir. It's an inverse Compton scattering, so it will boost the energy of CMB photons. And so it means that you will have a distortion of the CMB frequency spectrum. And as you can see on the left here, the signal, the TSZ signal has a very peculiar spectral distribution in frequencies. So it means that if we are able to trace the whole frequency distribution with multi-frequency observation, we can actually detect this signal very well. So what we are actually measuring is the amplitude of this distortion, that is the Compton parameter Y, that as you can see is basically the integral of the pressure profile of your gas distribution. And just to give you an idea, this is how the TSZ effect is actually tracing the underlying matter distribution. So we are actually able to trace quite well the dark matter below. We have different observations of TSZ already available from the different experiments. And what you see here is the full map coming from the Planck satellite back in 2015. Of course, we can do a power spectrum also from this map. And this is what you are seeing here. The red curve basically is the signal. And of course, I mean, with Planck, as we were seeing before, we are mainly focusing on the large scales range. So it means that we will be dominated by the objects that are providing the main signal, the largest structures. And these are actually the galaxy clusters. So you can see that the contribution of galaxy clusters here in green is the dominant one with respect to the total TSZ signal. And it's actually very easy somehow to detect galaxy clusters with TSZ, because as you can see, they really appear as a decrement and then increment in your frequency maps, basically. And this is an example of how well Planck was mapping the whole TSZ signal. But so it means that if we also have other experiments that can go to the large-scale regime, so the very right part of this plot here, we can go up to the arc-minute scales, and then be able to actually understand how TSZ can trace the smaller structures, so can it trace filaments or galaxy groups, etc. Of course, I mean, especially in this regime, we have to take care even more about how different astrophysical processes might shape the gas distribution. So, for example, if we have any kind of feedback or boost of energy that will boost the gas out of our structure, if we have an emerging process that is not having the equilibrium condition anymore. So all of this needs to be taken into account when studying the TSZ effect. So how do we model it? From a theoretical point of view, we can use the halo model. Halo model assumes that all your matter is distributed in halos. Of course, it's an approximation. As you can see, you have a top left, like what should be like the real view of your matter distribution, and then how the halos are actually tracing the underlying distribution. And we can decompose into the one halo term, so it's really looking at the signal inside your halo, or the two halo, that is the cross-correlation of signal from different halos. And you can see, therefore, that they will be the main contribution in the small or large-scale regime. But so since we want to study the halo distribution, the main ingredient is the halo mass function. So it's really your distribution in mass and redshift of the halos that you're considering. But then, as we were saying, we cannot trace it directly from our observables. And so we need a link that model the transition basically between the Compton parameter, in this case, and the underlying matter distribution. So you will have some kind of tracer in your halo model for the power spectra. And in this case, we are looking at something that is proportional to the pressure profile of your halos. So again, to the distribution of gas inside the halos. We can actually do cosmology just from TSZ power spectrum. These are results from back in 2018 from Planck only, but given all the new results that we have available now, it's surely possible to improve this kind of results. You have different curves here. Let's focus on the gray one on the top left. So what we're looking here are results for the omega m and sigma 8 parameters. These are cosmological parameters that describe the matter distribution in the universe. So omega m is the total matter density, and sigma 8 is telling us how the matter is clustering on different scales. As you can see, I mean, we have quite a huge banana in gray, of course. It's bigger than the other, but this was the case in which we were using only results from Planck, so focusing on the large scales, and then adding what was the amplitude of the template from SPT at the time. So we start to have a hint of how it will behave on smaller scales, but we need to cover the full range in order to improve these results. What you can also see in this plot is the results coming from the galaxy clusters. So we can focus just a bit on galaxy clusters to further understand the importance of TSZ signal for cosmological and astrophysical analysis. So the usual sentence for galaxy clusters is that they are the largest gravitationally bound structure in the universe. They are the peaks of the cosmic web. So it means that they are very useful in tracing the whole distribution of the cosmic web. They are formed mainly by dark matter and then hot gas and galaxies. And so it means that we can observe galaxy clusters in the whole electromagnetic spectrum. We have hot gas observations for millimeter and X-rays. We observe galaxies inside the clusters in optical and near infrared. We can use radio observation to study, for example, all the non-thermal processes. And then we can have also weak lensing observations. I mean, the lensing is the deflection of light due to a massive object. So using galaxy cluster that is supermassive will for sure produce a weak lensing signal. This is just a collection, I think not the most updated one, of the clusters detected with TSE observations in millimeter wavelength. As you can see, it's still the three experiments that we were talking about before. So it's still Planck, ACT, and SPT. And we are seeing kind of the same behavior as for the temperature and polarization power spectra. So we see that Planck is the red points here. It's good in the low redshift regime, while ACT and SPT, given that they have very deep observations, are actually able to detect clusters up to very high redshift. So you can see that already with what we have now, we are actually able to start to kind of cover the whole dynamical range of redshift evolution for clusters. But so the main point now is, assuming that we have our wonderful cluster catalog, how do we go from the detection to the actual constraints on cosmological parameters? And the idea behind is the same as we were seeing for the TSE power spectrum. So let's consider the number counts of clusters. This is the most widely used observable of galaxy clusters. So it's really counting objects, ideally in bins of mass and redshift. So it means that we start again from the halo mass function that should trace the underlying cosmological model. But then we need again something to relate this mass of clusters to what we are actually observing. So we need some kind of scaling relation that, of course, will help us in reconstruct the Y signal coming from these masses. And what is actually very cool about clusters is, as I was saying before, we can observe clusters in different wavelengths. And so it means that we can also combine these different observations to try to improve our modeling for the astrophysics that goes inside the scaling relations. And this is usually what is done when calibrating the scaling relation. And then the last ingredient, of course, in this case, I mean, we are talking about cluster detections. We will never be able to actually observe the whole cluster population that we have in the universe. And so we need to build this kind of selection function that will depend on the sky coverage, on the depth, but so understand how much we are complete in detecting our clusters, and also if we might have any possible spurious detection. So define the purity of our detections. Completeness and purity are therefore the main ingredients to build the selection function. So I will focus on the modeling of the scaling relations because this is always what links astrophysics and cosmology. Now, when we are talking about SE effect, we can actually make very simple assumptions. I mean, of course, we assume clusters to be spherical. We assume self-similarity. So it means that we assume that only gravity is driving the collapse of these objects. So it means that even if, of course, we will have some astrophysical processes that might deviate the gas distribution from this condition, we assume it to be fully negligible. And then we assume that the gas is fully in equilibrium in the potential well of the dark matter. And with this assumption, we have this very simple relation, top right, between Y and the cluster mass. And this was actually what was used, for example, already in Planck back in 2015. You have this complex scaling relation here, but I think that we can easily extract few information without focusing too much on the equations. So the cosmological sample for Planck was more than 400 clusters shown here. And then to further calibrate the scaling relations, we used observations in other wavelengths. So mainly in X-rays and weak lensing that would help us in fully calibrate the parameter of the scaling relation and then plug in this calibration into the cosmological analysis. The point is that, as you can see from this plot here on the right, you have very few clusters used for the calibrations. So, of course, not representative at all of the underlying cosmological model, but this is what was available at the time. And so, from this calibration, we get the results on cosmological parameters. I think most of you at least have seen these plots many times, so we can extract the main information from that. These are again constraints on omega m and sigma 8, so parameters for the matter distribution. And what is important to stress is that the three curves here in green, blue, and pink are all coming from the same cosmological sample, the same X-rays calibration, just changing the samples and values for the weak lensing calibration. So you can really see how much changing part of the scaling relation calibration is impacting a lot the final results on cosmological parameters. In particular, at the time, there was a tension between Planck anisotropies and Planck clusters, and one way to reconcile this tension, and so to push the results of clusters towards higher value of sigma 8, was to choose a specific value for this weak lensing calibration. But so the main point here are we have huge correlation between cosmological and scaling relation parameters, and this clearly reflects the interplay between cosmology and astrophysics in the cluster formation and evolution. And then we see that the choice of the calibration sample might impact a lot the results on cosmological parameters. So this was like 10 years ago. Lots of analysis also that we did at IAS have tried to improve this kind of results. But I think one of the results that I would like to show you today is really focusing on a new approach and a new sample for the calibration of the scaling relations. And so in particular, I'm going to show you results from this paper here that is led by Gaspar Aymerich. He was a former PhD student at IAS, and also in collaboration with the Dark Energy Survey. So the main idea is we want to improve the calibration sample and see if we can improve cosmological results. First of all, we change the X-rays calibration. The original one was from XMM. It was done selecting a sample that was just like the highest signal-to-noise clusters detected in X-rays that were matching with the Planck clusters. So it was a weird selection, very difficult to model, actually. In this case, we are using re-observations of Planck clusters from the Chandra satellite in X-rays. So as you can see from the plot, the red point over the black circles, we are way more representative on the underlying cosmological sample. This is an SZ selected sample because it was re-observations from Chandra with this goal. So this should already help us in improving our analysis. And then for weak lensing, we are using observation from the Dark Energy Survey. Now, in this case, instead of using this standard external calibration approach that we were using before, we are actually building the whole likelihood for the weak lensing measurement and combine it with the cosmological one from clusters. It means that we have really modeling, taking into account also the cosmological dependence of the all the probabilities going from the shear profile to the weak lensing mass to the SZ mass. And in the end, the final likelihood of the cosmological analysis will be the combination of the two, the weak lensing and the number counts. It means that we are also able to better quantify the error uncertainties coming from the weak lensing calibration into our cosmological analysis. Again, we had many results and details in this analysis. I'll just try to show you the main things. So if you look at the plot on the left, you should compare results in green with results in red. In green is the original Planck analysis. In red is the new results obtained with the full new approach and new samples for the calibrations. As you can see, especially if we focus on the 2D degeneracies of these parameters, we have a huge improvement in the results. That is really coming from the use of the new calibration approach. And then if you look at the plot on the left, The gray vertical band is our results, and is compared with other results from clusters and other results from other cosmological probes, for example, cosmic shear or CMB. So what you see is the fact that Planck clusters are still extremely competitive with the other results that we have nowadays in cosmology, and are therefore providing new results on this analysis. Of course, we are talking about stage 3 surveys in general. We are not even sure that for stage 4, the Planck data will still be competitive at the cluster level, but sure, this gives us a hint that there is still lots of information that can be extracted from this dataset to further improve the analysis. The last point that I would like to stress about the TSZ effect is the importance of the modeling and calibration of the pressure profile. This is really the key ingredient of our understanding of the signal. Of course, I mean, we can use the same assumptions that we are considering before for the scaling relations. We assume cluster to be spherical and in equilibrium, so the gas profile should follow exactly the dark matter profile of the halo. So we can assume like a generalized Navarro-Franken-White profile and then try to calibrate it on observations. Now, you can find lots of different pressure profile calibrations in literature, coming from X-rays alone, from SZ alone, from X-rays plus SZ, from numerical simulations. The plot on the top right is just like an idea of comparison of different profiles, and you can really see how they are, of course, normalized at the same point just to show even more the tilt that you can have in the inner or external part of your profile. And this is because what we usually do when fitting our profiles to the observations is, of course, fixing the cluster mass to some values that we can obtain from other observations, etc. But this will produce this kind of spread that you have here on the right, basically. While on the other hand, if we are able to fit at the same time the profile and the mass, because again, we want to understand how the mass measurements is linked to our observable, you can see that we are actually able to provide way more consistent results that take into account also our uncertainties on the mass measurements. And this is what was done in this paper led by Miren Munoz Echeverria, that is a former postdoc at IRAP in Toulouse. And as a last point, the pressure profile itself has impact on your cosmological results. Because, I mean, to detect clusters with SZ, we want to kind of filter the signal with to try to extract the peak of the signal to noise. And so filtering the signal, it means that you have to assume a profile. So you assume a pressure profile, and then your detection will totally depend on what you put into the modeling. It means that different profiles can actually change the completeness of your detection. And this is what was shown in this paper here led by Stefano Gallo. We see that for different pressure profiles, the color code is the same. We have different completeness and therefore different results on cosmological parameters. And these were shifting exactly in the same direction as the one that we were seeing before for the different weak lensing calibration. So you can really see that detection and understanding of astrophysics are completely related, of course, and are key ingredients in order to further develop the analysis of galaxy clusters and TSZ measurements in general. So we can now look at the other signal that is tracing the gas distribution in the recent universe. As of now, we have focused on the large-scale structure. We can go a bit back in time and focus on the reionization epoch. As we were saying at the very beginning, this is the formation of first stars and galaxies that will start to reionize the medium. So you have an easy depiction here going from the fully neutral medium after the formation of CMB to the first bubbles of reionization and then to the fully reionized medium that we have nowadays. So it's very important to describe the evolution of the ionized fraction in order to understand fully the reionization process. We can get different constraints from astrophysics, from CMB itself, but of course we know that, especially to characterize the reionization, we really need to wait for the upcoming 21 centimeter observations that will really improve a lot our understanding. But in the meantime, we can still look for other observables with what we have available now. And one of the ways to do it is through the kinetic Sunaya-Zeldovich effect. Still a secondary anisotropy, still interaction of CMB photons with electrons, but in this case, the boost in CMB energy will come from the bulk motion of the electrons with respect to the rest frame of the CMB. So with respect to TSZ, the signal is very, very low, as you can see here. And so it's already more difficult to detect. But in particular, we can split the total KSZ signal into two different contributions. The patchy one, that is really coming from the transition phase in which we have this kind of bubbles reionizing the universe. And so what is actually interesting is that so the signal that you can see here, the dashed line, is peaking at a scale that is roughly the average scale of these bubbles. And then we have the late contribution that is happening when the universe is already basically homogeneous in being reionized. And of course, as you can see, the signal from the late homogeneous part is way higher, so that when we are looking at the total signal, it is the dominant one. But it's very important to try to measure the patchy signal to further shed light on the whole reionization process. We can model it. There are lots of equations, but let's just focus on what is the electron power spectrum here. The idea is the same as we were seeing for TSZ. It's not Halo model, but it's anyway try to link the underlying distribution with your observable. And so in this way, basically your power spectrum from KSZ will be, of course, dependent somehow of the ionizing fraction that we were seeing before, so this XE here, but we can also try to split it into two different components. So this modeling was obtained in this work led by Adeli Gors in 2020 based on analysis from numerical simulations, but what they actually showed is that you can really try to apply this modeling to different kind of simulations, so with different input astrophysics, because there are some parameters that can be fitted. So what is very important is that, of course, you will have the low redshift part of the KSZ, in this case of the electron power spectrum, that is really a kind of a biased view of your total matter power spectrum, because we are looking at the universe that is fully ionized at this point. But what is really interesting is try to model the part of the patchy reionization. And as you can see here, we have two main parameters, alpha and kappa, where alpha is the constant amplitude and kappa is the drop-off in frequencies. So this ensures that we can actually apply this kind of parameterization to different simulations, but the problem is that these are not really physical parameters. So useful, but might not really help us in further understanding the astrophysics that is happening basically behind this the reionization phase. Okay, so now I've discussed at length about CMB, about TSZ, sorry. I gave you an idea, I hope, of what is the KSZ effect. And we've stressed a lot that both signals are carrying lots of cosmological and astrophysical information that it's important to model and understand, especially if we want to build a coherent modeling across scales and across times. But so it means that we can try to plug in this information into the CMB analysis. We were seeing at the very beginning that different choices of templates for this component might impact the final results. So what if we actually put the full modeling for these components inside the CMB analysis? And this is what we have been doing in these two papers that I'm going to show you now. In the first one, we have just substituted a template for TIZ with the actual full modeling based on Halo model. What is very important to stress is the fact that, of course, In both signal, CMB, primary anisotropies, and TSZ power spectrum, we have the same cosmology that is entering. And then in one case, for TSZ, we also have to take into account the astrophysics that is behind. So what we were using in this work, since we have seen that the templates have a really, the non-CMB components have a really dominant contribution in the small-scale regime, we focused on observation from the South Pole Telescope. So this paper is a bit old, so it is not the latest results from SPT, but it was still like the combination of SPT-SZ and SPT-Pole. And what we want to do is to see if we get any improvements in the results. So you have a collection of cosmological parameters, both on the left and right, and what you can see, 5 minutes, okay. What you can see on the left is the comparison between the case in which we are using the simple template that was used in the analysis in gray, and what happens when you actually plug in the TSZ modeling in blue. So you can see that we are already starting to improve the results on cosmological parameters because we are adding cosmological information coming from another components. And then on the right, you have the case in which we are adding TSZ observations also for Planck. So it means that for CMB primary anisotropies, we are just looking at the scales from SPT, but for TSZ, we have a coherent modeling spanning all scales. And these are the red and green curves. And as you can see, red and green are for different assumptions on the modeling of the scaling relation and pressure profile for TSZ analysis. But you can really see how much we are improving the results, especially if we improve also our understanding of astrophysics. The second results in this line of research is actually adding also the modeling for the KSZ signal. Now, in this case, both KSZ and the CMB primary anisotropies depend on the same cosmological model and on the same assumption for the reionization history. So, of course, you are bringing more information not only on the general cosmology model, but also on the specific part of the reionization. Same data set used before for SPT. We did different tests, but I think what is very interesting to stress here is the fact that for one of the first time, we're actually able to fully disentangle the patchy and late contribution for KSZ. And these results are marginalized over cosmological parameters. So it means that they are taking into account uncertainties of our model. We have a 5 sigma measurement of these two different components, and then it means that we can access directly the constraints on patchy reionization and try to go back to the astrophysical scenario. I mean, of course, CMB itself can already put constraints on the reionization history through the optical depth. This has been one of the key results from Planck for ages, the improvement on the constraints on tau, but especially if you're using Planck results alone, and we're focusing, as we were seeing, only on the large scales part, your measurement of tau will not really depend much on the reionization history. So it's very important to combine different scale observations to extract all the different constraints that we get on reionization. And as a very last point, I would like to go back for a second to the modeling of the KSZ, because we were seeing before, okay, we have quite a flexible model for the pressure power, for the electron power spectrum, but the parameters that we are putting in do not actually have a physical meaning. We have improved this analysis in this work led by Lisa McBride, in which we have tried to re-extract, again, the electron pressure profiles from a new set of simulations, but in this case, really highlighting how this electron power spectrum depends on the underlying astrophysics. And here you have an example of how the KSZ then can vary depending on the choice of different parameters. And in particular, the main impact that you have is for the plot bottom left for the ionized escape fraction. So basically how much the ionizing photon can be absorbed by the surrounding medium. But so it means that if we are plugging in astrophysical informations in CMB analysis, we can also do the other way around. And so it means that we can try to use CMB to actually obtain sensitive and meaningful constraints on the astrophysical parameterization. And this is what was done here. So this was, of course, a simple forecast analysis for stage 4 and the stage 4 plus CMB observations. But you can really see that we are actually able, with the CMB primary anisotropies and the modeling for KSZ, to put constraints on the astrophysical part. So I think I can go to my conclusions, and I'm perfectly on time, right? Okay, great. So I know I shared lots of information, and I'm happy to go into details for all the results that we have seen, but I also hope that I've convinced you of the importance of building a coherent modeling of cosmology and astrophysics across times and scales. This is one of the unique ways in which we have to really push cosmology to high precision science, to solve possible tensions that we have in our cosmological understanding. And CMB observations is one of the unique ways to do that, because we can really trace the whole evolution of the universe with that, tracing also, therefore, some astrophysical processes. I mean, of course, this is just the first step. We have listed many, many components at the very beginning. We have focused on TSZ and KSZ, but there is the CIB, there is the CO line, all of these things that still need to be modeled and improved, and this will be possibly the next step of this analysis. But I would really like to stress the fact that the whole CMB community is really moving in this kind of direction. So if you also have a look at recent results from ACT and SPT, that is the kind of approach that are starting to use to further improve their analysis. And I would just like to conclude with the fact that the INR has finished and all of our results are out, and you can go and have a look, in particular at the emulator that we have built with machine learning approach for the TSZ and KSZ observations. So you can go to this website, for example, in which you will find also many other products related to this science, and you are welcome to go, have a look, play with that, and get in touch if anything is not clear. Thank you.
Thank you. Is there any question? Don't hesitate. Let me check online.
Thank you for the nice talk. And I have just a curiosity on how is expensive to add the full modeling to the pipeline, because I imagine like just to run MCMC chain, how change with respect to just add a template.
It's very expensive, and that is exactly why we built the emulators for that. So the emulators are covering the whole parameters ranges that we can explore with TSZ and KSZ, and so we plug them into the analysis. So we are able to keep the dependence on cosmology and astrophysics, but especially in this case with SPT, we are going up to, I think, 13,000 in multiples. So integrating up to that scales is really heavy. So it was undoable without the emulators.
If I can, since and so of course, if you change the model, you need to train again your emulator. So how it works, or you have just some parameters that you can.
It depends how you change the model. So, for example, for TSZ power spectrum, the model that we have. It should work at all scales, but we know that we are talking about very, very different scales. So possibly something that works so if it's just tweaking the parameters, we should still be safe with those kind of emulators. If it starts to like add some further scale dependence because you need to mimic a bit more the scale evolution, etc., then you would need to retrain it. But I mean, the training part is not that long. It's just running the chains for the. I mean, running TSE and KSE themselves separately is not that long, so it's easy to produce the training set, basically.
Thanks. Is there any other question? I have one. Do you consider to add also bias about the shape of the cluster, like triaxiality and so on? Because you speak about the hydrostatic bias.
So it really depends on the analysis. When we are doing like the kind of external calibration approach, no, it's just spherical symmetry, and then of course it means that you call it hydrostatic bias, but then it's whatever bias that goes into the analysis. So it can also be this kind of shape measurement, etc. When we are doing the internal weak lensing calibration approach, in that case, since you are controlling directly the weak lensing measurement, you can marginalize over like miscentering, possible problem in the center definition, etc. So at least you should be taking a bit more into account uncertainties in that direction. But of course, this all needs to be improved with future observations also.
Okay, thanks. So can we imagine that given we put everything in this bias observationally, we could mimic it in simulation? Because for now, there is a gap between the hydrostatic bias in observation and simulation. So if in simulation we add all the bias, maybe it will solve.
Absolutely, absolutely. I mean, there are also high resolution observations, for example, from NICA 2 that are really showing what are the non-thermal contributions that you have entering the bias. But of course, numerical simulations, at least at this stage, is the only way to understand everything that is happening, that is entering into the hydrostatic mass bias, because you can really trace all the non-thermal contribution, you can trace mergers if they are impacting anything, you can trace triaxiality, etc. So that would be the best way. I still think that all of these are like percent corrections that goes to the total amount. So maybe with this data set, we can kind of say that it works, but for future, definitely. I mean, the importance of numerical simulations when we are doing astrophysics for cosmology is fundamental.
Okay, thanks. So any other question? Let's thanks again the speaker.
Thank you.